Before we start with the technical material, I want to tell you a little bit about the history of cryptography. There's a beautiful book on this topic by David Kahn called The Codebreakers that covers the history of cryptography all the way from the Babylonian era to the present. Here I'm just going to give you a few examples of historical ciphers, all of which are badly broken. So to talk about ciphers, the first thing I'm going to do is introduce our friends Alice and Bob, who are going to be with us for the rest of the quarter. So Alice and Bob are trying to communicate securely, and there is an attacker who's trying to eavesdrop on their conversation. So to communicate securely, they're going to share a secret key, which I'll denote by K. They both know this secret key, but the attacker does not know anything about this key K. So now they're going to use a cipher, which is a pair of algorithms, an encryption algorithm denoted by E, and a decryption algorithm D. These algorithms work as follows. The encryption algorithm E takes the message M as input, and it takes as input the key K. I'm going to put a wedge above the key input just to denote the fact that this input is really the key input. And then it outputs a ciphertext, which is the encryption of the message M using the key K. I'm always going to write the key first, and when I write :equals, what I mean is that the expression defines what the variable C stands for. Now the ciphertext is transmitted over the internet to Bob somehow. Actually, it could be transmitted over the internet, could be transmitted using an encrypted file system. It doesn't really matter. But when the ciphertext reaches Bob, he can plug it into the decryption algorithm and give the decryption algorithm the same key K. Again, I'm going to put a wedge here as well to denote the key input. And the decryption algorithm outputs the original plaintext message. Now, the reason we say that these are symmetric ciphers is that both the encryptor and decryptor actually use the same key K. As we'll see later in the course, there are ciphers where the encryptor uses one key and the decryptor uses a different key. But here we're just going to focus on symmetric ciphers where both sides use the same key. Okay, so let me give you a few historic examples of ciphers. The first example, the simplest one, is called a substitution cipher. I'm sure all of you played with substitution ciphers when you were in kindergarten. Basically, a key for a substitution cipher is a substitution table that basically says how to map letters. So here, for example, the letter A would be mapped to C, the letter B would be mapped to W, the letter C would be mapped to N, so on and so forth, and then the letter Z would be mapped, say, to A. So this is one example of a key for a substitution cipher. So just to practice the notation we introduced before, the encryption of a certain message using this key, let's say the message is B, C, Z, A, the encryption of this message using this key here would be, is done by substituting one letter at a time. So B becomes W, C becomes N, Z becomes A, and A becomes C. So the encryption of BCZA is WNAC, and this defines the ciphertext. Similarly, we can decrypt the ciphertext using the same key, and of course we'll get back the original message. Okay, so just for historical reasons, there's one example of something that's related to the substitution cipher called the Caesar cipher. The Caesar cipher actually is not really a cipher at all, and the reason is that it doesn't have a key. What a Caesar cipher is basically a substitution cipher where the substitution is fixed, namely it's a shift by 3. So A becomes D, B becomes E, C becomes F, and so on and so forth. What is it? Y becomes B, and Z becomes C. It's a fixed substitution that's applied to all plaintext messages. So again, this is not a cipher because there is no key. The key is fixed. So if an attacker knows how our encryption scheme works, he can easily decrypt the message. The key is not random, and therefore decryption is very easy once you understand how the scheme actually works. Okay, so now let's go back to the substitution cipher where the keys really are chosen at random. These substitution tables are chosen at random. And let's see how we break this substitution cipher. Turns out to be very easy to break. The first question is, how big is the key space? How many different keys are there, assuming we have 26 letters? So I hope all of you said that the number of keys is 26 factorial because a substitution key is simply a table, a permutation of all 26 letters. The number of permutations of 26 letters is 26 factorial. If you calculate this out, 26 factorial is about 2 to the 88, which means that describing a key in a substitution cipher takes about 88 bits. So each key is represented by about 88 bits. Now, this is a perfectly fine size for a key space. In fact, we're going to be seeing ciphers that are perfectly secure, that are adequately secure with key spaces that are roughly of this size. However, even though the substitution cipher has a large key space of size 2 to the 88, it's still terribly insecure. So let's see how to break it. And to break it, we're going to be using letter frequencies. So the first question is, what is the most frequent letter in English text? So I imagine all of you know that, in fact, E is the most common letter. And that is going to, if we make that quantitative, that's going to help us break a substitution cipher. So just given the ciphertext, we can already recover the plaintext. So the way we do that is, first of all, using frequencies of English letters. So here's how this works. So you give me an encrypted message using a substitution cipher. All I know is that the message is in English, the plaintext is in English. And I know that the letter E is the most frequent letter in English, and in fact it appears 12.7% of the time in standard English text. So what I'll do is I'll look at the ciphertext you gave me, and I'm going to count how many times every letter appears. Now, the most common letter in the ciphertext is going to be the encryption of the letter E with very high probability. So now I'm able to recover one entry in the key table. Namely, now I know what the letter E maps to. The next most common letter in English is the letter T, that appears about 9.1% of the time. So now again, I count how many times each letter appears in the ciphertext, and the second most frequent letter is very likely to be the encryption of the letter T. So now I've recovered the second entry in the key table. And I can continue this way. In fact, the letter A is the next most common letter. It appears 8.1% of the time. So now I can guess that the third most common letter in the ciphertext is the encryption of the letter A. And now I've recovered 3 entries in the key table. Well, so now what do? The remaining letters in English appear roughly the same amount of time, other than some rare letters like Q and X. But we're kind of stuck at this point. We figured out 3 entries in the key table, but what do we do next? So the next idea is to use frequencies of pairs of letters. Sometimes these are called digrams. So what I'll do is I'll count how many times each pair of letters appears in the ciphertext. And I know that in English, the most common pairs of letters are things like HE, AN, IN, I guess TH is another common pair of letters. And so I know that the most common pair of letters in the ciphertext is likely to be the encryption of one of these 4 pairs. And so by trial and error, I can sort of figure out more elements in the key table. And again, by more trial and error, this way, by looking at trigrams, I can actually figure out the entire key table. So the bottom line here is that, in fact, this substitution cipher is vulnerable to the worst possible type of attack, namely a ciphertext-only attack. Just given the ciphertext, the attacker can recover the decryption key and therefore recover the original plaintext. So there's really no point in encrypting anything using a substitution cipher because the attacker can easily decrypt it all. You might as well send your plaintext completely in the clear. So now we're going to fast forward to the Renaissance, and I guess we're moving from the Roman era to the Renaissance, and look at a cipher designed by a fellow named Vigenère who lived in the 16th century. He designed a couple of ciphers. Here I'm going to show you a variant of one of his ciphers. This is called a Vigenère cipher. So in a Vigenère cipher, the key is a word. In this case, the word is crypto. It's got 6 letters in it. And then to encrypt the message, what you do is you write the message under the key. So in this case, the message is, "What a nice day today." And then you replicate the key as many times as needed to cover the message. And then the way you encrypt is basically you add the key letters to the message letters modulo 26. So just to give you an example here, for example, if you add Y and A, you get Z. If you add T and A, you get U. And you do this for all the letters. And remember, whenever you add modulo 26. So if you go past Z, you go back to A. So that's the Vigenère cipher. And in fact, decryption is just as easy as encryption. Basically, the way you would decrypt is, again, you would write the ciphertext under the key, you would replicate the key, and then you would subtract the key from the ciphertext to get the original plaintext message. So breaking a Vigenère cipher is actually quite easy. Let me show you how you do it. The first thing we need to do is we need to assume that we know the length of the key. So let's just assume we know that. In this case, the length of the key is 6. And then what we do is we break the ciphertext into groups of 6 letters each. Okay, so we're going to get a bunch of groups like this. Each one contains 6 letters. And then we're going to look at the first letter in each group. Okay, so in this case, yes, we're looking at the first letter every 6 characters. Now, what do we know about these 6 letters? We know that, in fact, they're all encrypted using the same letter in the ciphertext. All of these are encrypted using the letter C. In other words, ZLW is a shift by 3 of the plaintext letters. So if we collect all these letters, then the most common letter among this set is likely to be the encryption of E. Right? E is the most common letter in English. Therefore, if I look at every 6th letter, the most common letter in that set is likely to be the encryption of the letter E. Aha! So let's just suppose that, in fact, the most common letter every 6th letter happens to be the letter H. Then we know that E plus the first letter of the key is equal to H. That says that the first letter of the key is equal to H minus E. And in fact, that is the letter C. So now we've recovered the first letter of the key. And now we can continue doing this with the second letter. So we look at the second letter in every group of 6 characters. And again, we repeat the same exercise. We find the most common letter among this set. And we know that this most common letter is likely the encryption of E. And therefore, whatever this most common letter is, if we subtract E from it, we're going to get the second letter of the key. And so on and so forth with the third letter every 6 characters. And this way we recover the entire key, and that allows us to decrypt the message. Now, the only caveat is that I had to assume ahead of time that I know the length of the key, which in this case is 6. But if I don't know the length of the key ahead of time, that's not a problem either. What I would do is I would run this decryption procedure assuming the key length is 1. Then I'd run it assuming the key length is 2. Then I would run it assuming the key length is 3. And so on and so on and so on until finally I get a message, I get a decryption that makes sense, that's sensical. And once I do that, I know that I've kind of recovered the right length of the key. And I know that I've also recovered the right key and therefore the right message. Okay, so very, very quickly you can decrypt Vigenère ciphers. Again, this is a ciphertext only attack. The interesting thing is that Vigenère had a good idea here. This addition mod 26 is actually a good idea, and we'll see that later, except it's executed very poorly here. And so we'll correct that a little bit later. Okay, we're going to fast forward now from the Renaissance to the 19th century, where everything became electric. And so people wanted to design ciphers that use electric motors. In particular, these ciphers are called rotor machines because they use rotors. So an early example is called a Hebern machine, which uses a single rotor. Here you have a picture of this machine. The motor, I guess the rotor is over here, and the secret key is captured by this disk here. It's embedded inside of this disk, which rotates by 1 notch every time you press a key on the typewriter. Okay, so every time you hit a key, the disk rotates by 1 notch. Now, what does this key do? Well, the key actually encodes a substitution table. So, and therefore the disk actually is the secret key. And as I said, this disk encodes a substitution table. In this case, if you happen to press C as the first letter, output would be the letter T. And then the disk would rotate by 1 notch. After rotating by 1 notch, the new substitution table becomes the one shown here. You see that E basically moves up, and then the remaining letters move down. So imagine this is basically a 2-dimensional rendering of the disk rotating by 1 notch. Then you press the next letter, and the disk rotates again. You notice again N moved up, and the remaining letters moved down. So in particular, if we hit the letter C 3 times, the first time the output would be T. The second time the output would be S, and the third time the output would be K. So this is how this single rotor machine works. And as it turned out, very quickly after it was advertised, it was again broken basically using letter frequencies, digram frequencies, and trigram frequencies. It's not that hard given enough ciphertext to directly recover the secret key and then the message. Again, a ciphertext only attack. So to kind of work against these frequency attacks, these statistical attacks, these rotor machines became more and more complicated over time until finally, I'm sure you've all heard of the Enigma. The Enigma is kind of complicated rotor machine. It uses 3, 4, or 5 rotors. There are different versions of the Enigma machine. Here you see an example of the Enigma machine with 3 rotors. The secret key in the Enigma machine is the initial setting of the rotors. Okay, so in the case of 3 rotors, there would be 26 cube possible different keys. When you type on the typewriter, basically these rotors here rotate at different rates. Oh, I forgot to say this is a diagram of an Enigma machine using 4 rotors. As you type on the typewriter, the rotors rotate and output the appropriate letters of the ciphertext. So in this case, the number of keys is 26 to the 4th, which is 2 to the 18, which is actually relatively a small key space. Today you can kind of brute force search using a computer through 2 to the 18 different keys very, very quickly. You know, my wristwatch can do it in just a few seconds, I guess. And so this Enigma machine was using relatively small key spaces, but I'm sure you've all heard that the British cryptographers at Bletchley Park were able to mount ciphertext-only attacks on the Enigma machine. They were able to decrypt German ciphers back in World War II, and that played an important role in many different battles during the war. After the war, I guess that was the end kind of the mechanical age, and started the digital age where folks were using computers. And as the world kind of migrated to using computers, the government realized that it's buying a lot of digital equipment from industry. And so it wanted industry to use a good cipher so that when it buys equipment from industry, it would be getting equipment with a decent cipher. And so the government put out this request for proposal for a data encryption standard, a federal data encryption standard. And we're going to talk about this effort in more detail later on in the course. But in 1974, a group at IBM put together a cipher that became known as DES, the Data Encryption Standard, which became a federal standard for encrypting data. The key space for DES is 2 to the 56, which is relatively small these days, but was large enough back in 1974. And another interesting thing about DES is rather than, unlike rotor machines, which encrypt 1 character at a time, the data encryption standard encrypts 64 bits at a time, namely 8 characters at a time. And we'll see the significance of this later on in the course. Because DES uses such a small key space, these days it can be broken by a brute force search. And so these days DES is considered insecure and should not be used in projects. Unfortunately, it is used in some legacy systems, but it definitely is on its way out and definitely should not be used in new projects. Today, there are new ciphers, things like the Advanced Encryption Standard, which uses 128-bit keys. Again, we'll talk about the Advanced Encryption Standard in much more detail later on in the course. There are many, many other types of ciphers. I mentioned Salsa 20 here. We'll see why in just a minute. But this is all for the quick historical survey. And now we can get into the more technical material.